When people think about the most dramatic phenomena in space, they immediately jump to black holes. And for good reason. Gravity so extreme it pulls even light back in. Absolutely mind-bending. But neutron stars deserve far more attention than they get. A neutron star is also born when a massive star dies, but without quite enough mass to collapse into a black hole. Instead, it leaves behind an actual physical object. Something real. Something you can study. While a black hole is essentially a bottomless void, a neutron star is this bizarre, tangible thing you can observe, measure, and analyze. And what you're looking at is so extreme that our current physics struggles to fully describe it. The raw power of neutron stars is almost beyond comprehension. One of the deepest mysteries in all of science is the question, what exactly is energy? Most of us understand it in everyday terms. It takes energy to throw a ball, chemical energy from your muscles, or an object sitting at the top of a hill holds potential energy, ready to release as it rolls down under gravity. But then there's the energy locked inside matter itself. And here's where things get truly strange. Light, pure energy, and matter, made of protons, neutrons, and electrons, seem like completely different things. Yet modern physics tells us something deeply unsettling. They're not. Mass and energy are essentially the same thing. Mass is just energy in a dense, stored form. You can convert one into the other and back again. That's the legendary equation Einstein gave us. E equals mc squared. Inside any amount of mass hides an equivalent amount of energy. The universe barely distinguishes between the two. Nuclear fusion is a perfect example. Particles slam together, forming larger atoms, and in the process a tiny amount of mass vanishes, converted into enormous bursts of pure energy. It works in reverse too. Inside a particle accelerator, particles collide at incredible speeds, generating so much energy that brand new particles spontaneously pop into existence. That's how physicists discover new particles, pump in enough energy, and the universe converts it directly into mass. Energy equals mass times the speed of light squared. That conversion factor is enormous. But the truth is stunning. Energy and mass are fundamentally the same thing wearing different faces. One of the most mind-blowing ways the universe operates involves something called virtual particles, the energy embedded in space and time itself. The raw, inherent energy of the universe can actually transform into mass. It spontaneously generates what are known as virtual particle pairs, like an electron and its antimatter counterpart, a positron. These two particles literally burst into existence because enough energy surrounds them. And then, almost instantly, they destroy each other. Matter and antimatter colliding in a flash of pure energy. This is happening everywhere around you, right now. All throughout space, these tiny virtual particles are constantly flickering in and out of existence. But the truly extraordinary things happen when those particles get pulled apart. Take a neutron star. Its magnetic poles can fire powerful beams of energy, generated by virtual particles that are ripped apart and accelerated by an insanely strong magnetic field. Suddenly, energy that didn't exist before is being produced by the virtual particles themselves, at extreme energy levels, like those found near neutron stars with their unimaginably powerful magnetic fields. These virtual particle pairs are created in staggering numbers. The more energy present, the more virtual particles appear, until space itself begins to behave as though it has mass. The density of virtual particles surrounding a neutron star, even in what should be empty space, would be roughly 3 times the density of iron. That is absolutely staggering. Energy and mass are truly the same thing. Two sides of the same coin, endlessly convertible into each other. The universe treats them as one. So why do we call it a neutron star? In a normal atom, protons and neutrons sit in the nucleus while electrons orbit at a distance. But the gravity of a neutron star is so crushingly powerful that it forces those electrons directly into the nucleus. Smash a negatively charged electron into a positively charged proton, and the result is a neutron. What you're left with is an object composed almost entirely of neutrons. Essentially one enormous atomic nucleus, about 10 miles across. 10 miles. The density of an atomic nucleus stretched across 10 miles. It's almost incomprehensible. And because of the extreme collapse involved in their formation, the conservation of angular momentum kicks in dramatically. Think of an ice skater spinning with arms stretched wide. The moment she pulls them in, she spins faster and faster. The same principle applies here, but on a cosmic scale. The result is a ball roughly 10 miles across, spinning 500 times every single second. Just wrap your mind around this. Something that massive, spinning that fast. It's almost impossible to comprehend. Now, neutron stars have recently played a crucial role in solving one of the biggest mysteries in modern astronomy. A mystery so deep, so baffling, that some scientists actually wondered whether what we were detecting could be signals from an advanced alien civilization. We're talking about fast radio bursts. Fast radio bursts have dominated headlines for years, and for good reason. These mysterious explosions of radio energy were so extreme, so violent, that nobody could explain them. Imagine this. A radio telescope picks up a burst of emission lasting just 1 millisecond, 1,000th of a single second. And yet, in that razor-thin slice of time, the energy released rivals everything our sun produces in an entire week, in a millisecond. These signals were coming from all across the sky, and the scientific world was desperate for answers. How could anything unleash that much raw energy in such a tiny window of time? The race was on. Fortunately, we have powerful tools at our disposal. Right now, high-energy telescopes orbit Earth, detecting X-rays and gamma rays, the most extreme forms of light in the universe, produced only when matter reaches temperatures of millions or even billions of degrees. And as researchers began pinpointing exactly where these bursts were coming from, something remarkable emerged. They lined up with neutron stars. Neutron stars are almost certainly the source of fast radio bursts. The exact mechanism is still being unraveled, but the leading theory involves something like a starquake, similar to an earthquake here on Earth, where shifting crustal material sends powerful waves rippling through the planet's interior. In fact, that's precisely how we've mapped Earth's inner structure, from a liquid metal outer core to a solid metal inner core, without ever physically sampling it. We simply track how compression waves travel through the planet. The same principle may apply to neutron stars, but on an almost unimaginably violent scale. Picture a sphere of pure neutrons, compressed to staggering densities at extreme temperatures. Scientists believe a crystalline crust of neutrons forms on the outside of these stars, while the interior churns as a fluid of pure neutrons. We know this because neutron stars, as they spin, sometimes wobble, almost like a water balloon sloshing in slow motion. The gravity near that crust would be so crushing, so absolute, that it would reduce any object, any material, to subatomic particles instantly. But what happens if that crust develops a flaw? When a quake strikes and the crust shifts and reshapes itself, it sends powerful compression waves rippling through the neutron star, unleashing tremendous bursts of energy in a fraction of a second. And right now, our best explanation for these astonishingly mysterious fast radio bursts is that they are neutron starquakes. Just like earthquakes have revealed so much about the deep interior of our planet, scientists are now dissecting these signals. Even within 1,000th of a second, they pull that signal apart, searching for hidden structure buried inside that burst of radiation, trying to reconstruct what the inside of a neutron star actually looks like. Neutron stars are real cosmic monsters. Unlike black holes, you can actually see them. You can observe their surfaces and map the radiation pouring off them. When it comes to the most mysterious and measurable objects in the universe, neutron stars are absolutely worth your attention. The closest neutron stars are still hundreds or thousands of light years away, so thankfully they pose no threat to us. But here's a fascinating question. How close could you actually get to one before the radiation simply obliterated you? Or in the case of a neutron star, something even stranger might get you first. Most people know Einstein's famous equation, E equals mc squared, which tells us that energy equals mass times the speed of light squared. What that really means is that inside even a tiny amount of mass, there is a staggering amount of energy locked away. The nuclear bombs dropped on Japan converted roughly the mass of a small coin into pure destructive energy. So the mass of a single finger contains the equivalent of countless nuclear warheads worth of energy. But E equals mc squared works in reverse too. Enormous amounts of energy can actually start behaving like mass through something called virtual particles. Pack enough energy into a small enough space, and the universe itself begins spontaneously creating real particles whose mass matches that energy. Energy literally becomes matter. This is exactly how particle accelerators work. Smash two gold nuclei together at extreme speeds, and the collision produces so much energy that particles begin popping into existence from pure force alone. Given enough energy, you can create virtually any particle the universe contains, emerging in all different varieties as long as the energy budget allows it. Neutron stars are doing something remarkably similar, acting as nature's own particle accelerators, powered purely by their own crushing gravity. The gravitational contraction is so extreme that the electric and magnetic fields of the star get compressed around this incredibly tiny object. The result is magnetic fields trillions of times stronger than any refrigerator magnet you've ever touched. Fields so powerful they would literally tear ordinary matter apart on contact. The magnetic fields surrounding a neutron star contain almost unimaginable amounts of energy. Think about Einstein's famous equation, E equals mc squared. The magnetic energy concentrated around a neutron star is so extreme that the vacuum of space itself begins generating virtual particles. And here's the mind-blowing part. That vacuum, a place where normally nothing exists, reaches a density roughly 3 times that of pure iron, simply from the sheer number of virtual particles being produced by that magnetic field's energy. Just imagine flying around an object where empty space itself is 3 times denser than solid iron. What would that even look like? What would it feel like? Seeing a neutron star from a safe distance, whatever that distance might be, would be one of the most extraordinary experiences imaginable. These are real objects, existing right now in the night sky above us. We can't see them because they're dim, tiny, and incredibly far away. But their high energy radiation is washing over us constantly. These things are absolute cosmic monsters. Our own sun also blasts out a relentless wind of high energy particles. This was only discovered relatively recently. The very first satellites launched in the late 1950s and 1960s detected unexpected radiation and particles flooding through space. That discovery was largely predicted by a brilliant scientist named Eugene Parker, after whom the Parker Solar Probe is named. That spacecraft is currently orbiting closer to the Sun than any human-made object in history, and it's revealing extraordinary new details about how the solar wind actually works. This wind carries electrons, protons, and sometimes particles as large as helium nuclei, all blasting through our solar system at speeds reaching 1,000,000 miles per hour. That relentless stream of energy has dramatically shaped every world in our solar system. It's responsible for stripping Mars of its atmosphere, turning it into the cold, barren desert we see today. It transformed Venus into the hellish, toxic world it's become, blasting away lighter molecules like water and leaving behind a suffocating atmosphere of carbon dioxide and sulfuric acid. Even distant Pluto, sitting at the very edge of our planetary system, is losing tons of atmosphere every single day, blasted away by this relentless stream of high-energy particles. The only reason Earth escapes serious damage is because of our incredibly powerful magnetic field. The molten metal churning deep inside our planet generates a kind of magnetic bubble around Earth, and that bubble shields us from the solar wind. But make no mistake, someday the sun will ultimately blast away our atmosphere entirely. Planets change. And understanding this wind is absolutely critical, because we need to know exactly what we're dealing with out there in space. Under normal conditions, the solar wind produces radiation levels that humans can handle with ease. Now, conspiracy theorists love to ask, how did we ever land on the moon with all that deadly radiation out there? The truth is, we got lucky with Apollo. On a typical day, radiation levels in space or on the lunar surface are completely manageable for human beings. The real danger comes from solar storms. Violent, explosive events that unleash massive bursts of solar wind. We call these coronal mass ejections. The corona is the outermost layer of the sun's atmosphere, and during one of these events, an enormous amount of material erupts all at once. If a powerful ejection hits in the direction of unprotected astronauts, far from Earth's magnetic shield, it could deliver a fatal dose of radiation. That is a terrifying reality we cannot ignore. Remarkably, between several Apollo missions, massive solar events occurred that would have endangered any astronauts on the moon. We dodged disaster by pure chance. This is exactly why traveling to the moon, and eventually Mars, demands serious radiation protection. The good news? It's not impossible. A sufficient volume of water could actually shield astronauts effectively. A water tank aboard a spacecraft could serve as a life-saving barrier. The challenge is the sheer mass required to launch it. On the moon, digging just about 10 feet below the surface would provide enough rock coverage to protect people. But that means hauling construction equipment capable of tunneling through lunar soil. These are the extraordinary challenges being tackled right now. Now, something even more spectacular happens out in deep space. Imagine 2 massive stars locked in a binary system, orbiting close to each other, each one blasting out its own powerful stream of particles. We call this a stellar wind, because these aren't just any stars. These are giants. Monsters carrying anywhere from 20 to 50 times the mass of our sun, generating winds far more ferocious than anything our sun produces. When those 2 stellar winds collide, something breathtaking occurs. Electric and magnetic fields become violently entangled. Particles slam into each other at incredible speeds. The result is an extraordinarily hot region we call a shockwave. As all that material crashes together and slows down, enormous amounts of heat and radiation are unleashed along that shock front. One of the most powerful natural phenomena in the entire universe. Those are stunning shockwaves created by colliding solar winds. So one of the biggest challenges right now, especially as we consider sending astronauts back to the moon, is this. Can we actually predict when one of these violent events is coming? The answer is yes, in several ways. In the simplest sense, we have spacecraft already out there. Right now, 2 probes are orbiting the Sun, the Parker Solar Probe and the European Solar Orbiter. We also have other spacecraft positioned between Earth and the Sun. When one of these massive eruptions of charged, high-energy particles blasts out from the Sun, it hits different satellites that measure its speed and energy output. In the case of the Moon, Earth typically gets about 1 to 2 days of warning. That's enough time to alert astronauts. Get inside, find shelter, stay protected, as long as proper shelter exists. But the real question is, can we predict it before it even happens? That is one of the greatest goals driving scientists around the world known as heliophysicists. Physicists who dedicate their lives to studying the Sun. The Sun is an extraordinary magnetic marvel. Magnetic fields are generated by moving electric charges. Similar to how moving metal in an engine produces a magnetic field. In the Sun's case, it's made almost entirely of hydrogen, but the surface is so incredibly hot that the gas becomes ionized. There's so much energy that electrons, which normally orbit a nucleus, simply break free, leaving behind 2 charged particles, an electron and a proton. Anything carrying an electric charge can be bent by a magnetic field. Those breathtaking loops and swirling shapes visible on the Sun? That's superheated, electrically charged gas, called plasma, flowing along the Sun's magnetic field lines. The Sun's magnetic field is visible in those loops, but it is wildly chaotic and mind-bendingly complex. So how do scientists predict when one of those loops will suddenly snap open and violently hurl material into space, triggering one of these massive ejections? We're getting better, but we still don't fully understand it. Something as fundamental as our own star, and we still can't predict a major solar storm down to the hour. Scientists can identify an active region that looks threatening, but there's no way to guarantee what it will do. This actually brings to mind the year 2012, when widespread panic gripped the public over the so-called Mayan apocalypse. That year supposedly marked the end of a major cycle in the Mayan calendar, and people became convinced something catastrophic was imminent. Calls flooded into NASA. Desperate, frightened people asking unthinkable questions. Some callers were genuinely asking whether they should euthanize their pets before the end came. People would ask things like, "Is the world going to end next month?" And the answer was always the same. Look, if anyone actually knew the world was ending next month, they certainly wouldn't be sitting in an office answering phone calls. The reassurance was clear. There was absolutely nothing unusual happening astronomically. The Sun was simply in one of its naturally active periods. Every 11 years or so, the Sun ramps up its activity, then gradually quiets back down again. One of the most breathtaking signs of this activity is the northern lights, the auroras. These stunning glowing displays around the poles are created when charged particles pour into our atmosphere. For most of us on Earth, that's really the only dramatic effect we ever notice. But what actually occurred was something truly staggering. A colossal coronal mass ejection, one powerful enough to seriously threaten our power grids here on Earth. It wouldn't have harmed people, animals, or plants directly, but it would have dumped enormous electric currents into our magnetic field, potentially taking down power infrastructure on a massive scale. The saving grace? It fired off from the opposite side of the Sun, away from Earth entirely. Satellites positioned out in that direction took the full brunt of that enormous burst of charged particles. Scientists tracked it, studied it, and collectively breathed a huge sigh of relief. Here's what makes this even more fascinating. The Sun doesn't spin as one solid object. Its equator rotates faster than its poles, causing it to twist and contort itself. On average, it completes one rotation roughly every 29 days. That means a dangerous active region could suddenly spin out of Earth's line of fire, or something catastrophic could emerge from the far side completely unseen. This is the wild, complex world of space weather. Not gentle breezes, but particle winds and magnetic storms of pure chaos erupting from our nearest star. It's almost impossible to believe that the soft, warm light we enjoy every day comes from something so ferociously dramatic and unpredictably volatile.